Now I'm going to talk about 4 techniques in molecular biology: PCR, RFLP, TACMAN, and sequencing. So first, PCR. PCR stands for polymerase chain reaction. It is a technique to amplify a DNA region of interest and is essential to molecular biology. PCR was invented by Dr. Kary Mullis in 1983, and I encourage you to check out the PCR song. How does PCR work? First, I'm going to talk about the reagents needed for PCR. You have buffer, which contains ions to keep the DNA stable and the enzymes working. You must have a DNA template, and this is what is amplified in the PCR reaction. Primers define the segment of DNA you want to amplify. The enzyme is only able to bond to double-strand DNA, so this controls where replication will start, but I'll talk more about this later. Nucleotides serve as the building blocks of a new strand of DNA, and it is the polymerase that actually builds the new strand of DNA. The polymerase is from a thermobacteria, Thermus aquaticus, and that's where it gets its name, TAC. And the reason for this is so that it's not denatured in the heating and cooling process that is required for PCR. There are 3 stages in PCR: denaturing, annealing, and extending. This animation will help to illustrate how PCR works. The first step is denaturing. This occurs at a high temperature, usually around 95 degrees Celsius. The high temperature will cause the DNA double helix to unwind and become single-stranded. The next stage is annealing. In this step, the temperature of the reaction is reduced. Annealing temperatures range from about 50 degrees Celsius to 65 degrees Celsius, depending on a variety of factors. In the annealing stage, the primers bind to the complementary sections of DNA. For a good PCR, these primers should bind to only one location in the genome. The final step is extending. The temperature is increased to about 72. As I stated before, Taq polymerase is only able to bind to double-stranded DNA. Now that the primers have bound to the DNA template, the polymerase can bind to the DNA and will add nucleotides to the primer, forming a complementary DNA strand. These 3 steps are repeated a number of times, vastly amplifying the amount of DNA. PCR is a little complicated, so we're going to watch another cycle of PCR. Again, you see the DNA is denatured at 95 degrees Celsius, the temperature is reduced, so primers will anneal to the template, and the temperature is increased, so Taq polymerase will bind and create complementary DNA. Now in the third cycle, you can see we have the first PCR products that contain only the region of DNA of interest. Now the video is going to speed up quite a bit. So you can see that the DNA region of interest is amplified by orders of magnitude more than anything else. This is another interesting benefit of PCR. Since that DNA region of interest is amplified so many times, PCR is almost a purification technique. The concentration of that DNA region of interest is so much higher than anything else. Everything else is virtually trivial.